So we've seen how you can take a ketone, react it with a primary amine, and get an imine, a Schiff base. What if, though, instead of having a primary amine, instead of having two hydrogens and only one carbon chain, you had a secondary amine? So two carbon chains and only one hydrogen available. Well, in that case, you wouldn't be able to do this last proton transfer step. You wouldn't be able to get rid of the second hydrogen, to form a second bond here. And so you don't form an imine anymore. You don't form that second bond there. Oops. You can still form the first bond because it can take the place of that original hydrogen. And you can now you have this other carbon there. And you do still do this proton transfer, you just do it at a different position. You'll see that you end up forming this pi bond there. Now, everything else about the mechanism is exactly the same except for the last step. And the last step is still a proton transfer. It's just the hydrogen that is being transferred that's different. So if you have a secondary amine, the product is different. All the steps are the same going around. Even the carbonylamine that you get will be exactly the same. Well, except you'll have the two carbons on there, the carbon chains on there. The one difference is where you do this proton transfer at the very end. Now the product that you form here, this is described as an enamine. It's an enamine, en because you have a double bond, and amine because you have an amine. So pretty straightforward, an enamine. So in your head, you want to organize it. If you have a ketone and a primary amine, you form an imine. But if you have a ketone and a secondary amine, you form an enamine. Okay, let's see how this works in a mechanism. We'll start off with this first mechanism here, and you can see we have an enamine here, a double bond, and with an amine coming off of it. So we're forming that double bond, and you'll notice that the amine that we use to form that is a primary amine. It's a secondary amine. It has two carbon chains coming off of it. So let's fill in this table. This is the same exact table as we used for imine formation. We want to draw in our ketone or our aldehyde. We want to draw in the enamine that we're going to form. Oops. And then let's see if we can picture the carbonylamine. Now we're taking two bonds to oxygen, we're replacing them with a bond to a nitrogen, and then this other pi bond here. So we'll still have one bond to the oxygen there in the carbonylamine, but we'll have another bond going to the amine. Now, the secondary amine we have, just to draw it out clearly, is a nitrogen bonded to a hydrogen, and it has two ethyl groups. That's what that ET2 is telling you. So that's one ethyl group and another ethyl group. Okay, so this is our general outline. This is the procedure we're going to follow. Let's think about how this happens. We'll start with our ketone and our secondary amine. Just like before, the nitrogen is slightly negative. We can't add an acid to make this happen faster, to protonate the ketone, because the amine will act as a base and turn into an ammonium ion, and then it wouldn't act as a nucleophile. So you'll want the pH to be somewhere around 4.5, so that this exists in an equilibrium with an ammonium ion. There's still this molecule to react, and there's still some catalytic acid that we can use. And that is what they're giving us here. They give us the sulfuric acid in brackets. That's really catalytic sulfuric acid. You'll see, you put that into water, it all turns into hydronium. All of the strong acid gives its H+'s away. Water accepts it, so you have hydronium there, and you'll see that we use that in this mechanism. But the first step is noticing the carbonyl carbon is slightly positive, the oxygen slightly negative, And our nitrogen is slightly negative, so it can act as a nucleophile and attack the carbonyl carbon. The pi bond breaks, the electrons go on the more electronegative atom. The closest electronegative atom nearby, that's that oxygen. So that's our first step, nucleophilic attack. Now after that first step, what we'll have is just one bond to the oxygen, but now that will have a full negative charge. Right? It had 2 lone pairs before, now it has 3 and a full negative charge. And now you have one bond to the nitrogen, which still has a hydrogen, and has 2 ethyl groups. That nitrogen has 4 bonds, and so it has a positive charge. It is an ammonium ion. So we have a lot of charges that we need to stabilize. And we're going to do that, stabilize those through proton transfers. First, we mentioned how we have acid in the solution, and the acid we're going to use is hydronium. They give us sulfuric acid, but when you put sulfuric acid in water, all the sulfuric acid gives its hydrogens away, and so the effective acid that's in water is hydronium. The negative oxygen can pluck off one of these slightly positive hydrogens. The electrons snap back onto the oxygen to stabilize its positive charge. So we did a proton transfer. We're taking this hydrogen and moving it from the hydronium ion onto our molecule. And the result of that will be pretty much the same, except this oxygen now won't have a full negative charge, and one of its lone pairs will turn into a bond to hydrogen. So we've helped to stabilize that molecule a little bit. Notice the hydronium also turns into a water. And we can use that water as a base to stabilize the other positive charge, or the other charge here. We can do a proton transfer, take the slightly negative oxygen, have it steal the slightly positive hydrogen. The electrons snap back onto the nitrogen to help stabilize that positive charge. So that's another proton transfer. We're transferring this H+ proton from one molecule to another. And that gives us a molecule that has no charge. It gives us the carbanolamine. Now notice, this carbon is bonded to both an alcohol and an amine. And so that is the definition of a carbanolamine. A carbon bonded to both an alcohol and an amine. Well, if you compare the carbanolamine with the enamine that we're trying to form, you'll see that the OH has to go. It doesn't stick around. And so we need that to leave. But right now, it's a terrible leaving group. So we can do a proton transfer to turn it into a better leaving group. In this previous step, we formed H3O+. So that can act as an acid and the slightly negative oxygen can attack one of those slightly positive hydrogens. The electrons snap back onto the oxygen there. Now after that proton transfer, our molecule looks very similar, just one of the lone pairs there have turned into a hydrogen, and that gives oxygen a positive charge, so that's our oxonium ion. And now that oxygen is an amazing leaving group. All it needs is a small push, and the push is provided by the nitrogen. The carbon in between the oxygen and the nitrogen is pretty slightly positive. It's losing its electron density to both of those very electronegative atoms. And so this slightly negative nitrogen is very attracted to it. It tries to use its lone pair to form another bond. Those electrons want to go toward that positive charge. Up until now, they've been pushed back, but now that you have a good leaving group, they kick the leaving group off, and you get loss of a leaving group. The molecule that you have left has a double bond to the nitrogen, and the nitrogen has 2 other R groups, so it has a full positive charge there. And we also form water. All right, well, that nitrogen is not stable. It has a full positive charge. So we have to figure out how to stabilize it. And we're going to do the same last step as you would normally do in imine formation, but this is where things get a little different. Notice that there's no hydrogen on the nitrogen to steal. We can't do a proton transfer off of the nitrogen. But there is a vulnerable hydrogen nearby, and that is right here. Now, where you have the carbonyl, or where you have the double bond, that would be considered like the carbonyl carbon here. But right next door, that's called the alpha position, and this is called the alpha hydrogen. The alpha hydrogen is slightly acidic, because if it leaves the molecule, then the lone pairs that are left behind, the electrons that are left behind, are allylic to the pi bond, and so they can be spread out and stabilized through resonance. Well, that's all we need. That hydrogen is a little bit vulnerable, and so we can take this base, have the base steal that alpha hydrogen, the electrons snap toward the nitrogen, and the pi bond kicks up onto the nitrogen to stabilize the positive charge. And when we're left, what we're left with after the dust settles there, is a pi bond between the alpha position and what was the carbonyl carbon, and then a nitrogen with no charge in a lone pair. Now, this should remind you also of elimination. You remember that in elimination reactions, you also take that neighboring hydrogen and use its electrons to kick a leaving group off. In this case, the leaving group is just pi electrons. And they stay on the molecule, but they go away from the pi bond that you're forming. So that should remind you a little bit of elimination reactions. But you could see that ultimately what we form is an enamine. A pi bond, so double bond ene, with an amine coming off of it. And the mechanism is exactly the same as imine formation. It's just this last step that's different. Now, imine formation also has a proton transfer here, but the proton is is something coming off of the nitrogen, whereas here it's in enamine formation. You have a secondary amine, so there's no second hydrogen on the nitrogen. So the next most vulnerable hydrogen is the one next door on the alpha position, and that forms an enamine. Okay. So if we were to review that whole reaction, just a quick overview of what we did. The amine, secondary amine, so we see secondary amine and instantly we think, we're going to form an enamine. The secondary amine attacks the carbonyl carbon, nucleophilic attack. That creates a couple charges. The negative charge on the oxygen is stabilized by a proton transfer. The positive charge on the nitrogen is also stabilized by a proton transfer. That gives us the carbonylamine. We want the OH off, so we turn it into a better leaving group with a proton transfer. It gets kicked off, we have loss of a leaving group because the nitrogen forms a double bond. And then we just stabilize the nitrogen by stealing this neighboring hydrogen, and we form the enamine. Okay, same process, let's think through that with just slightly different reagents. Notice that we have an enamine, right? We have a double bond with an amine coming off of it. And another sign, a sign that this would be an enamine formation, is they give us an amine that is secondary. It's bonded to 2 carbons. So let's draw our molecules in. We have a ketone that we're going to start with. We have an enamine that we will end up with. And our secondary amine is dimethylamine. So that looks like this. 2 methyl groups coming off of the nitrogen. Now the carbonylamine, that will still have 1 bond to the oxygen. The oxygen will be an OH now. And it'll have 1 bond to the secondary amine. The only thing missing from that will be the hydrogen. So that is a carbon with an amine on it and an alcohol. Both of those groups on the same carbon, that's a carbonylamine. So this is our overall plan. If we ever get lost, we can look back at this. Okay, I've written out these steps, these curved arrow patterns. I've written them out one by one. I encourage you to do the same when you draw out the mechanism. So we're going to have the first step, nucleophilic attack. That's going to occur between the carbonyl and the secondary amine. The carbonyl carbon is very slightly positive. It's losing its electrons to the oxygen, which is slightly negative. The amine, nitrogen, is slightly negative. So it can swoop in and attack the carbonyl carbon, kick the pi electrons onto the oxygen. When it does, so that's our nucleophilic attack. When it does that, we have the same carbon skeleton. We have an oxygen, whereas it had only 2 lone pairs before, now it will have 3 with a full negative charge. The nitrogen has 2 methyl groups and a hydrogen on it. That nitrogen has 4 bonds, so it will have a full positive charge. So we have a lot of charges on this molecule. We're going to stabilize them by doing proton transfers. Now they've given us an acid. In this molecule they gave us sulfuric acid. They're putting it in brackets because they're trying to say that it's catalytic. When you put the sulfuric acid in water, though, all of the H2SO4s give their hydrogens away, and the molecule that accepts them is the water. So now the effective acid you have is hydronium. Now, the negative oxygen can steal one of the slightly positive hydrogens, and they're especially vulnerable because the electrons can snap back. They're attracted to the very positive oxygen and hydronium. After that proton transfer, we would have this molecule, but it won't have the negative charge anymore. And instead, that oxygen will have a hydrogen bonded to it. So we've taken care of one of the charges. We've gotten rid of them. And notice we also form a water here. The hydronium that lost its hydrogen turns into a water. Well, we can use that water as a base. It can swoop in, the slightly negative oxygen can swoop in and steal the slightly positive hydrogen. The electrons go onto the nitrogen to help stabilize that positive charge. And so here we're doing a proton transfer to help to stabilize the charge. What we're left with after that is our carbonylamine. Let me change it. So we won't have this hydrogen anymore, and the electrons that were going to it just form a lone pair. So that's our carbonylamine. We have a carbon with an alcohol and an amine attached to the same position. We're halfway there. We just need to get rid of this OH. But right now it's a bad leaving group, so we have to do a proton transfer to turn it in to a better leaving group. Well, in the last step, we formed hydronium. The slightly negative oxygen steals the slightly positive hydrogens. The electrons snap back and go onto the oxygen to help stabilize it. So now, we've done a proton transfer. We've put a hydrogen on our carbonylamine so that it'll turn in to a better leaving group. The OH will turn into a better leaving group. And that's what happens. You get this extra hydrogen here. That oxygen now has a full positive charge. It's described as an oxonium ion. Well, now it's a good leaving group. All it needs is a small push. The carbon in between the oxygen and the nitrogen is losing electrons to both, so it's slightly positive. The nitrogen next door, slightly negative. The electrons there are attracted to the positive charge. They try to form a bond. Normally, they're pushed back by the other bonds to that atom. But now, the leaving group is so good that it takes its electrons and it gets kicked off the molecule. So that is loss of a leaving group. And what you get after that step is a water on the side and on the molecule we're going to have a double bond to the nitrogen, which has those 2 methyl groups. Well, here we're at this, everything so far has been the same as when we do imine formation with primary amines. But here we have a secondary amine. Notice this nitrogen has a positive charge because it has 4 bonds, so it's an ammonium ion. Here we have a secondary amine, and we can't stabilize that positive charge with a proton transfer from the nitrogen. We have to get the proton from somewhere else. And we do it in the alpha position. This would be considered like the carbonyl carbon. Right next door is the alpha carbon. We're going to take a hydrogen from that alpha position. Those alpha hydrogens are acidic because the hydrogen can pop off and the electrons are allylic to this positive charge. So it doesn't take a strong base. Even water can pluck the hydrogen off. The electrons go toward the carbonyl carbon and they kick one of the pi bonds. They kick the pi bond onto electrons onto the nitrogen. Now ultimately this is a proton transfer. We're moving a hydrogen from one molecule to the other, but it's not a hydrogen on the nitrogen. There isn't one there because it was a secondary amine. It's a hydrogen on the alpha position, one carbon away from the double bond. And so what we're left with here is a double bond going toward the nitrogen, a single bond from the carbon chain to the nitrogen, and the two methyl groups with a lone pair. And so that is the final molecule. That is your enamine that you would get. Enamine that you would get from this reaction. So to recap what we did there, we followed all the same steps as for imine formation, but we watched out because we had a secondary amine. We do nucleophilic attack with the secondary amine. That produces charges. We stabilize the negative charge with a proton transfer. We stabilize the positive charge with a proton transfer. We want to kick the oxygen off. It's a bad leaving group, so we make a better leaving group with a proton transfer. We'll note that that's the carbonylamine. Once it's off, the neighboring nitrogen can, once it's a good leaving group, the neighboring nitrogen can kick it off. We have loss of a leaving group. And we just have to stabilize the nitrogen with a proton transfer. In the case of secondary amines, you take off the alpha hydrogen because there's no hydrogen on the nitrogen, and that leaves you with the enamine. So hopefully these last two examples have given you some sense of how enamines can be formed.